Hello everyone, I am Jyoti Patil, lecturer EC department, unit 2 in ARM instruction set, lecture number 15. The contents those will be discussed in this session are data processing instructions which are being continued. So next is logical instructions. Logical instructions perform bitwise logical operations on the two source registers. These instructions update CPSR flags only if the S suffix is present. These instructions can use barrel shifted second operands in the same way as that of arithmetic instructions. The syntax of logical instruction is shown. The first logical instruction which we will be studying here is AND. It does the logical bitwise AND of two 32-bit values. RD is equal to RN ampersand N. This instruction will perform a logical AND operation between the two operands, placing the result in the destination register. This is useful for masking the bits you wish to work on. Operand 1 is a register, operand 2 can be a register, shifted register or an immediate value. For example, AND R0, R1, R2. R0 is equal to R1 and R2. And R0, R1, hash 0 cross 0 0 0 8 0 0. In this, R1 is ANDed with the immediate value and then the obtained result is stored in destination register R0. And R0, R2, R3 LSL hash 1. In this, R3 is shifted to the left by one position, then it is ANDed with R2 and the obtained result is stored into R0. The next instruction is ORR, that is OR operation it performs. It does logical bitwise OR of two 32-bit values, that is RD or N. This instruction will perform a logical OR between two operands, placing the result in the destination register. ORR R0, R1, R2. R0 is equal to R1 or R2. ORR R0, R1, hash 0 cross 8 0 0. This instruction, in this, R1 is ORed with the immediate value and then the result is stored into R0. Next is ORR R0, R2, R3 hash LSL hash 1. In this, R3 is left shifted by one position, then that is ORed with R2 and then the result is stored in R0. The next instruction is EOR. It does logical exclusive OR of two 32-bit values. That is RD is equal to Rn dot N. That is Rn XOR N. This instruction will perform a logical exclusive OR between the two operands, placing the result in the destination register. EOR R0, R1, R2. R0 is equal to R1 XOR R2. EOR R0, R1, hash 0 cross 8 0 0. In this, R0 will be equal to R1 XOR 0 cross 8 0 0. Next is EOR R0, R2, R3 LSL hash 1. That is, R3 is left shifted by one position and then it is exclusively ORed with R2 and the result is stored in destination register R0. The next instructions will be comparison instructions. The comparison instructions are used to compare or test a register with a 32-bit value. They update the CPSR flag bits according to the result but do not affect other register. After the bits have been set, the information then can be used to change program flow by using conditional execution. CMP. The first comparison instruction is CMP, that is compare. The CMP instruction performs subtraction but does not store the result. In this, only flags are always updated. The syntax for CMP is shown. The next instruction is CMN, compare negated. CMN is same as CMP except it allows you to compare against small negative values. The syntax for which is shown. The next comparison instruction is TST, which is test. This instruction performs a non-destructive AND. It performs a logical AND operation between operand 1 and operand 2. The result is not stored, but the flags are always updated. TST R0, R1. Whenever Z flag is equal to 1, then R0 will be equal to R1. Otherwise, it will be equal to 0. That is, if the contents of R0 and R1 are same, then Z flag will be equal to 1. If not, it will be equal to 0. Next, TST R0, hash 0 cross 80H. If Z is equal to 1, the 15th bit of R0 will be equal to 0. Otherwise, it will be 0. The next instructions are multiply instructions. The multiply instructions multiply the contents of a pair of register. Depending upon the instruction, the result is stored in another register. The long multiples accumulate onto a pair of register representing a 64-bit value. The final result is placed in a destination register or a pair of register. MUL, that is multiply. This instruction performs a 32 cross 32 multiply operation and stores a 32-bit result. MUL R2, R1, R0. Let R0 is equal to 0 cross 00002. R1 is equal to 0 cross 00004. R2 is equal to 0 cross 600H. After execution of this instruction, R2 will be equal to R1 into R0. So, after multiplying R1 into R0, we get R2 as 0 cross 0008. The next instruction is MLA, multiply and accumulate. MLA behaves the same as multiply instruction, except the value of the operand 3 added to the result. The syntax for which is shown. Example MLA R3, R2, R1, R0. This instruction adds the product of R1 and R0 to R0 and stores the result in R3. Thank you.